Okay, welcome everyone to today's seminar. Our speaker today is Professor Koji Fukagata. He is a professor at Department of Mechanical Engineering at Keio University in Japan. He has worked on diverse fields in fluid mechanics, including flow control and machine learning, and he has served as an editor of Flow, Turbulence, and Combustion, and he's currently a director of the Japan Society of Fluid Mechanics and a vice chairman of the Fluids Engineering Division of the Japan Society of Mechanical Engineers. His talk today is about turbulent friction drag reduction, and I will leave it to him.
Okay, thank you very much for the kind introduction. I'm Koji Fukagata from Keio University, Japan. Today, I'd like to talk about turbulent friction drag reduction by feedback and predetermined control approaches. As you may know well, the friction drag in turbulent flow is much larger than the laminar flow at the same Reynolds number. And the larger drag means that more energy is wasted as heat through the larger dissipation. And as you may know well, this larger friction drag in turbulent flows is due to the enhanced exchange of momentum by these quasi-streamers vortices. Thanks to the success of DNS or wall turbulence in 1980s, many DNS studies have been conducted to reduce friction drag in wall turbulence by means of feedback control. The simplest idea is to reduce the friction drag to suppress these quasi-streamers vortices. And this is a basic idea of so-called opposition control proposed by Choi et al. In their numerical experiment, they assumed wall normal velocity sensors placed above the wall, and the actuation is done by blowing and suction continuously distributed on the wall so as to oppose these quasi-streamers vortices. And they attained about 20% drag reduction in DNS of low Reynolds number turbulent channel flow. And sorry, this was stopped. Sorry. Wait. Yes. This animation shows the opposition control turbulent pipe flow, which I simulated about 20 years ago. As time goes, you can see that these red and blue quasi-streamers vortices are suppressed by the blowing and suction from the wall, indicated by yellow and green. And also you can see that the friction drag is reduced accordingly, like this. The opposition control is okay as a numerical experiment, but in reality, one cannot place sensors above the wall. So different approaches have been proposed to substitute this idealization. The first approach is to assume control law and optimize the parameters contained in that control law. Using, for example, neural network or genetic algorithm. Actually, this genetic algorithm was used also in our wind tunnel experiment, as will be shown in the next slide. And the second approach is to use a control theory so that the control effects similar to the opposition control can be attained using the wall shear stress sensor placed on the wall only. And the third approach is to use the state estimation techniques such as Kalman filter, neural network, and Taylor expansion to estimate the velocity above the wall. And this is a feedback control system used in the wind tunnel experiment, which was developed in the national project in Japan, in which I was involved about 20 years ago when I was a postdoc and research associate. Here we have 48 wall shear stress sensors in one row with a span-wide spacing of about 12 wall units. And we have four rows of such sensors. And also we have 16 electromagnetic actuators in one row, which can produce wall normal velocity on the wall. And we have 3 rows of such actuators. And we have prescribed a control law so that the electric voltage applied to the actuators expressed as a weighted sum of signals from these sensors. And we optimized the weighting factors by using the genetic algorithm so as to minimize the drag. In the actual wind tunnel experiment using this device, we have confirmed about 6% drag reduction. The feedback control worked reasonably well in the wind tunnel experiment, but there is a big issue towards its practical application, namely the physical diameter and frequency of quasi-string vortices. This figure shows the physical diameter and oscillation frequency of quasi-streamers vortices in different applications. For example, when we consider turbulent flows that develop on the surface of bullet train or aircraft, the typical diameter of quasi-streamer vortices will be on the order of 0.1 millimeter, and the frequency will be on the order of 10 kilohertz. It means that we need such small and fast responding sensors and actuators to interact with the quasi-streamer vortices. But as shown here, which shows a range that can be attained by different types of actuators, there is no actuator in principle which can cover this range at the moment. And so far, we have introduced some examples of feedback control, which uses sensors, actuators, and controller like this. Feedback control is, of course, potentially effective, but there is a big hurdle for hardware development, as we have seen. Another candidate is so-called predetermined or open loop control without sensors. With this type of control, the control input is determined irrespective of the detailed flow state, so it should be easier to realize. But the question is how we should determine this control input. To start with the predetermined control, let us consider the relationship between friction drag and turbulence statistics for fully developed incompressed channel flow called FIK identity. The friction drag coefficient CF is decomposed into laminar drag and the turbulent contribution, which is a weighted integral of the Reynolds shear stress. This equation suggests that even if we do not know anything about vortices, if we can reduce the near wall Reynolds shear stress, then we can reduce the drag. And actually, several researchers, including myself, have attempted control based on this idea. Here, I assumed feedback body force to reduce the Reynolds shear stress, and the research group at UCLA, John Kim's group, used upstream traveling wave of blowing and suction. In both cases, drag lower than the laminar flow, called sublaminar drag, was obtained in DNS. By the way, it was later proved mathematically that this sublaminar drag is not beneficial in terms of energy saving, and the relaminarization is the best in terms of energy saving. And this is a result obtained by Min et al. For a laminar flow. The horizontal axis is a phase speed of the traveling wave, and the vertical axis is a drag increment, which is the same as the turbulent contribution term in the FIK identity. As you can see here, the downstream waves always increase the drag, regardless of the wave number of this traveling wave. In contrast, downstream waves, which is negative phase speed, this term can become negative for several parameters, suggesting negative Reynolds shear stress. This is also the result obtained by Min et al. In the DNS of turbulent channel flow. With the upstream traveling wave, like this and like this, the drag becomes even below the laminar value. And in such case, the Reynolds stress near the wall is highly negative, as shown here. And this slide explains the reason for the negative Reynolds shear stress with the upstream traveling wave of blowing suction. The wall normal velocity V distribution is kind of direct response to the blowing and suction from the wall. And the induced streamwise velocity U prime is mostly orthogonal to V away from the wall, but it has some phase shift near the wall due to the viscosity. And actually this phase shift eventually produce negative Reynolds shear stress. To summarize, the primary drag reduction mechanism by traveling wave like blowing suction is like this. The wave of blowing and suction traveling upstream in the upstream direction produces negative Reynolds shear stress, and it induces the net flow in the downstream direction, which is known as a pumping effect. As a result, the external pressure gradient required to keep the flow rate constant is reduced, which is observed as a drag reduction. Of course, turbulent modification is accompanied too. And actually, the drag is reduced also by downstream traveling wave of blowing suction. And this is a result obtained by in DNS of turbulent channel flow by Mamori et al. Two different friction Reynolds numbers under constant pressure gradient conditions. And this result suggests that downstream waves traveling faster than the mean flow can relaminarize the flow, which is indicated by red region. When the wavelength is on the order of 100 wall units in both Reynolds numbers, and the phase speed much higher than the flow speed. And this is the result of receptivity analysis done by Molev and Jovanovic. And the painted region identify the value of phase, speed, and frequency omega that suppress the energy amplification of both most energetic modes and the least stable modes. It is also confirmed by this receptivity analysis that a downstream wave, this one, traveling faster than the mean flow, can stabilize the flow. Whereas the upstream wave corresponding to Min et al. Case destabilize the flow. Actually, the traveling wave like blowing suction device is still difficult to make in practice. And actually, Min et al. Who proposed the upstream traveling wave, also mentioned about it in their paper like this. However, a moving surface with wavy motion would produce a similar effect, since wavy walls with small amplitude can be approximated by surface blowing suction. So the next question is whether it can simply be substituted by wall deformation like this. But we found that not upstream but downstream traveling wave like this would produce a similar effect in the case of wall deformation. This is due to the difference in the direction of pumping effect. This animation shows the comparison of pumping effect in the case of blowing suction and wall deformation. In the case of wall deformation, we can observe that the fluid particles indicated by black points move from left to right like this, namely in the direction same as the traveling wave. In contrast, in the case of blowing and suction, the fluid particles move from right to left, which is the opposite direction against the traveling wave, like this. So as a result, the net flow is induced in the same direction as a traveling wave in the case of wall deformation, and the opposite direction in the case of blowing and suction. As we have seen, the pumping effect is in the case of blowing and suction takes place in the direction opposite to the wave, so the upstream wave reduces the drag. In contrast, the pumping effect in the case of wall deformation is in the same direction as the wave, so the downstream wave is expected to reduce the drag. As for the stability or receptivity, flow is stabilized by a downstream wave of wall normal velocity on the wall, as we have seen. From this, we can expect that in the case of wall deformation, a downstream wave is expected to reduce the drag due to both pumping effect and stability. Although this kind of analysis for wall deformation case is still ongoing. But from the knowledge from the velocity analysis, it can be said like that. And this animation shows DNS with downstream traveling wave like wall deformation. Starting from a node deformation, when the wall starts to deform, the quasi-streamwise vortices are suppressed like this. And span-wise roller-like structure appear instead. And this figure shows a time trace of mean pressure gradient under different parameter sets for the wave. This is a node deformation case. And this is an upstream traveling wave, which results in drag increase. And these are the downstream traveling wave cases. In this green case, the drag is reduced, but the flow remains turbulent. In the red case, the drag approaches to the laminar drag, suggesting relaminarization. In this blue case, the drag decreased toward the laminar drag, but suddenly it becomes unstable and again decreases like this. And this is a map showing the drag reduction effect on the different sets of parameters. The horizontal axis is a deformation period, T plus, and the vertical axis is a deformation amplitude in wall units. We can see that relaminarization, the red region, is observed when the deformation amplitude is about 10 to 20, around 10 wall units, and the deformation period around 10 or 20 wall unit time. And the flow becomes unstable, like this blue line, when the wall displacement gets larger than this. In the present case, the maximum drag reduction rate, which is written as numbers here, was 69%. And the net power saving rate that also accounts for the power required for actuation was 65%. This is a summary of the drag reduction mechanism by downstream traveling wave like wall deformation. In this case too, the negative Reynolds shear stress is produced, and it works to pump the flow in the same direction as a wave. And the external pressure gradient required to keep the flow rate is reduced, which is observed as drag reduction. And when the deformation amplitude is not too large, it leads to relaminalization due to the stabilization effect. But when the deformation amplitude is too large, it destabilizes the flow due to this kind of inflectional instability. And it leads to a periodic oscillation in drag. And this slide shows a Reynolds number effect of traveling wave like wall deformation. As we can see here, the mean velocity profile of the controlled flow, these ones, are well scaled in wall units, regardless of the Reynolds number studied here. And from this result, we can also develop a theoretical model to predict the drag reduction rate at much higher Reynolds numbers. According to such prediction, we can still expect about more than 20% drag reduction at very high Reynolds number appearing in many industrial applications. Actually, in this case, the DNS, the drag reduction rate obtained by DNS is a bit higher than the theoretical model, but this is kind of a low Reynolds number effect. Now we are doing LES at even higher Reynolds number, and we have confirmed that these simulation result will approach to the model at higher Reynolds number, although not shown here. The effect of this traveling wave like wall deformation is also investigated in a wind tunnel experiment by a group at Tokyo University of Agriculture and Technology. They placed a rubber sheet. It's difficult to see here, but here is a rubber sheet visualized by laser sheet here, and on the channel wall, and actuated it using a piezo actuator, single piezo actuator like this, so that the wall deformation travel in the downstream direction like this. And they have also confirmed by PIV, I guess, PIV, and measure the velocity profile. And they have confirmed the drag reduction effect through this piezo-driven traveling wave like wall deformation. Okay, this is a short summary on drag reduction by streamwise traveling wave. We have considered streamwise traveling waves of wall blowing suction and wall deformation. And upstream traveling wave of wall blowing suction achieves sublaminar drag due primarily to the pumping effect, but the flow is destabilized. The downstream traveling waves of wall blowing suction and wall deformation at the phase speed higher than the flow speed reduce the drag by stabilizing turbulent flows. In the case of wall deformation, the optimum parameters are wavelengths of about 300 wall units and maximum deformation of 15 wall units. Actually, by going back to the slide previously, this one. 300 wall units is approximately 10 times this value. So in the case of bullet train or maglev aircraft, it still needs, the size is still like 1 millimeter wavelength. So it is still small. So in order to realize this kind of control, we have to develop this kind of system which can generate 10th or 100 waves by single piezo actuator. Otherwise, it is impossible to realize in practical application. Okay, and substantial drag reduction effect can be expected even at high Reynolds number. Here are some future issues. Drag reduction and net power saving effects, the higher Reynolds number needs to be investigated further. And the drag reduction effect is still unclear for external flows, for example, for spatial developing turbulent boundary layers. And this is what I said right now. Although larger than those targeting a separation of QSVs, the size of actuator required in practical application is as small as 1 millimeter. So some novel material or additional working principle may be needed. Okay, I would like to introduce some other attempts on predetermined control. First, uniform blowing. It is well known that very weak uniform blowing and suction from the wall significantly modifies the wall turbulence. And this is a vertical structure in a turbulent boundary layer with uniform blowing at 1% free stream, 1% of free stream velocity. In this case, the turbulence is enhanced as compared to the no control case, but the drag is actually reduced. This is somewhat contradicting result, but it can also be explained by using this FIK identity. Actually, in this case, 1% uniform blowing case, the turbulent contribution, this dark gray one, is increased due to the enhancement of turbulence like this. But the negative contribution due to the mean wall normal flux is very much increased in the negative direction. As a result, the total friction drag indicated by this red line is reduced as compared to the uncontrolled case. We have also used this uniform blowing for drag reduction of airfoil in our wind tunnel experiment like this. And we have measured the velocity in the boundary layer using this hot wire anemometer. This is a result of our most recent wind tunnel experiment. In this case, the uniform blowing is applied on the pressure side of the airfoil. And this figure shows the friction drag coefficient as a function of streamwise location of the airfoil, where C denotes the chord length, and the green indicates the blowing region here. As we can see here, the friction drag is significantly reduced by the uniform blowing, like this, at both angles of attack, 0 degree and 6 degree. And the drag reduction effect slightly remains in the downstream region too, due to the thickening of the boundary layer. This is another experiment on uniform blowing. In this case, the air used for uniform blowing is possibly taken from the leading edge of the airfoil, so that we don't need any external pump or blower. The intake as well as blowing region is covered by the perforated metal plate, and in addition, porous film is attached on the blowing region in order to ensure the hydrodynamically smooth surface. And this is the obtained friction drag coefficient as function of streamwise location. In this case, actually, we place the blowing region on the suction side, different from the previous one. And as we can see here, the drag is substantially reduced in this case too. And also, this experimental result agree well with the simulation results. And so far, I have mainly talked about predetermined control, but actually, I I have been working for feedback control for more than 20 years, perhaps, and I still cannot give up the possibility of feedback control. So we are still trying or still studying feedback control. Our one of the recent attempts for more effective feedback control is to utilize resolvent analysis, which I think is very famous in Australia, right? And the governing equation can be rearranged as a following response, forcing response relationship like this. And the response to the forcing is represented by this resolvent operator. The forcing response gain is obtained by applying singular value decomposition, SVD, of this resolvent operator. And this singular value suggests whether the mode is amplified or suppressed, something like that. And previous study have shown that first mode is often significant. So we also consider this rank 1 mode. First, we investigated the singular values in the case of suboptimal control proposed by Lee et al. And case SP refers to the case where the span-wise shear is used as a sensor signal. And case ST refers to the case where the streamwise shear is used as a sensor signal. In the DNS study by Lee et al., case SP successfully reduced the drag, but case ST resulted in drag increment or no change. Here is a result of our resolvent analysis. In case SP, significant suppression, this red region, is indicated in the region corresponding to the near wall cycle. And there is almost no change in the other region indicated by green. In case ST, using a streamwise wall shear, significant suppression is also indicated in the region corresponding to the near wall cycle like this, but shorter streamwise wavelengths are indicated to be highly amplified. I mean, the negative value means the amplification of the mode, highly amplified like this. And remember, in the DNS study of Lee et al., case ST did not reduce the drag. So we think that the reason of that failure can be this detrimental effect in this region A. We performed DNS to see whether such detrimental effect emerges in real flows. This figure shows the contour of the blowing and suction on the lower wall. In the case SP, which uses a span-wise wall shear and which resulted in drag reduction, the structures are long in the streamwise direction and exhibit alternating region of positive blowing and negative blowing velocity in the span-wise direction. And this observation confirms that case SP is targeting at the quasi-streamwise vortices associated with a near wall cycle. On the other hand, in case ST, which uses streamwise wall shear, the blowing and suction contours are more elongated in span-wise direction and becomes very much shorter in streamwise direction. In other words, the control input does not seem to be targeting or interacting with the near wall modes, near wall structures. So it is not exact. anything is near wall structure, but what we call near wall structure, right? Okay, so the reason why this case ST did not work can be attributed this kind of energetic and weird span-wise structure. From such observations, we proposed a new control law named case STZ. We have just modified the wave number here from kx to kz. I mean, streamwise wave number to spanwise wave number, so as to avoid a strong negative value here for the short streamwise waves. This figure shows a resolvent-based prediction for case STZ. I mean, changing kx to kz. And we did the same analysis, the resolvent analysis. And the effect around the near wall cycle is nearly unchanged, but the amplification for the short streamwise wavelengths is very much suppressed like this. And we have confirmed this effect in DNS. And this is a result of DNS showing the time trace of mean pressure gradient to key the flow rate. I don't talk much detail about the difference between CA and CL and CS, but the overall result is this black line CA. Unlike case ST, about 10% drag reduction is obtained by using only the streamwise wall shear as a sensor information. Okay. How much time I have? Maybe 5 minutes more. Okay, 5 or 10 minutes more. Another example, another attempt is the application of machine learning, which has also been investigated in my research group under these Japan Society of Promotion of Science Kaken projects. Our aim is to apply machine learning to flow field data, extract nonlinear features, and find the governing equation, and eventually propose a new flow control method based on the extracted features. And this is a basic structure of the machine learning model we are mostly using. The network is based on CNN autoencoder. The flow field is low dimensionalized by the encoder part of the CNN, and the part in the middle does some operation depending on the purpose, like extraction of a feature or extraction of a governing equation or control law, whatever. And the flow field is recovered from the low dimensional latent vector using the CNN decoder like this. The convolutional neural network is widely used not only in image processing, but also in the fluid flow field data. And especially CNN autoencoder is often used to low dimensionalize the flow field as we are doing. But what is actually obtained by this kind of CNN autoencoder? Here we consider a statistically steady periodic flow around the circular cylinder at Reynolds number 100 and low dimensionalize the flow field into only two latent variables like this. And especially in order to visualize the contribution of each latent variable, we decode each variable separately like this using this tailored network structure, which is called MDCNN, model decomposing CNN autoencoder. This slide shows a comparison of velocity fields we constructed using the first two modes obtained by different techniques. This is a reconstruction using TOD, two modes, and these MDCNN linear and MDCNN tan-H are the machine learning model, but this MDCNN linear use linear function for all activation function. So the network itself is linear. And tan-H uses hyperbolic tangent function for the activation function in all layers except for the last layer. So this is kind of usual or ordinary neural convolutional neural network. The upper figures shows an instantaneous field of streamwise velocity, and the lower figure shows the time average error as compared to the reference DNS. And as we can see here, the reconstruction results by POD and MDCNN linear are quite similar to each other, and the error, time average error, is also similar. And the error, yeah, actually the error, time average error is very much reduced by using the nonlinear convolution neural network like this. Actually, this was for the streamwise velocity component, but the same can be observed for the vertical velocity component. And this result suggests that the CNN autoencoder is basically similar to POD. But the nonlinear activation function included in the network works to improve the reconstruction with a given number of modes. To see what is contained in the two modes, two autoencoder modes extracted by nonlinear CNN, we apply the POD again to the collection of the reconstructed field. Although I will skip the detailed explanation, it has turned out that a single nonlinear low-dimensional mode contains multiple POD modes, so that better reconstruction from the same number of modes is possible with a nonlinear CNN. Once we can low dimensionalize the flow field, then we can also derive the governing equation for the low dimensional dynamics. This is an example of a transient flow around the circular cylinder at the Reynolds number 100. In this case, we can low dimensionalize the flow field to two variables like this, and we can derive a nonlinear ordinary differential equation for the low-dimensional autoencoder modes using the technique called Cindy, proposed by Steve Brunton's group. And we have also confirmed that, actually, we have also confirmed not only to cylinder flow, but also for the 9-equation turbulent shear flow model. Once the governing equation for the low-dimensional dynamics is mathematically expressed like this, it is also possible to combine it with a modern control theory, for example, to stabilize the flow like this. Here is our preliminary attempt on the feedback control based on CNN Cindy. We consider a flow around the circular cylinder at Reynolds number 100, and we assume a blowing suction on the surface of the cylinder like this. In the training process, we train the CNN autoencoder under various flow fields by varying the actuation amplitude M. Then we derive the low-dimensional dynamical equation, including this actuation magnitude, actuation amplitude M. Then, by applying the optimal control theory to this latent dynamics with the help of coordinate transformation, we obtain a feedback control law to stabilize the trajectory of the latent variable like this. The flow field in the physical space is recovered by using this CNN autoencoder, decoder, and we can confirm that the wake is successfully stabilized by this feedback control. And this is more recent attempt. This is more recent attempt on machine learning based feedback control using what we call linear system extracting autoencoder, LEAE. LEAE is composed of an encoder and two decoders sharing the weights and the linear ordinary differential equation layer, LODE layer. And the training is done for both reconstruction at the same time step and the time evolution described by the linear ordinary equation in the latent space. The most important feature of this model is that this LODE layer represents time evolution of latent vector. After LEAE, this LEAE is trained without control input. We perform additional training with some prescribed control inputs like this. Here we assume blowing suction as a control input, and blowing suction are fixed at 100 degrees from the stagnation point as before, and the magnitude is determined by the control parameter m. At this stage, we fix the system matrix A, which has already been identified at the first training stage without control input. And we here train this control matrix B only. And once the system matrix A and B, control matrix B are identified in machine learning, then we can derive the control law in the latent space using a linear quadratic irregulator as usual like this. And this is a DNS result of feedback control using this LEAE. The control input is updated on every 100 time step of DNS, which corresponds to 1/20th of the vortex shedding period. And this is the animation of the streamwise velocity. Blue is faster, red is slower. Although it is not very clear from this velocity counters, from this animation, quantitative measure like the lift coefficient, it confirms that the fluctuation is suppressed like this. Anyway, we are still in the halfway of this kind of research, and we are continuing this kind of study toward more toward application to more complex flows, eventually turbulent flows. Okay, let us summarize my talk. Extensive investigation has been made on turbulence control since DNS has matured in late 1980s. While feedback control succeeded at least theoretically and numerically, a big hurdle still remains in the hardware development. And predetermined control has a great potential too, and higher possibility of practical application. The remaining issues are further development of control methods, which are more suitable for practical implementation, including application of machine learning, and of course, hardware development. And we are currently tackling with these issues. And okay, this is the end of my talk, and many of the topics I introduced today were summarized in these review papers. Please take a look if you are interested. Thank you very much, and I'm happy to take questions. Thank you.
Thank you for the very interesting talk. Please feel free to ask your questions either through turning on your video or through the chats.
Van is raising a hand.
Yes. Good afternoon, Professor Kota. Can I have a question about the Thank you for a very interesting presentation.
Thank you.
And can I have a question about the uniform blowing control?
Okay.
And when you say that when we use the uniform blowing control, we have the increase in turbulence, but we
Yeah.
still have the drag reduction.
Mm.
So can you give more detail about the increase in turbulence? Is that the turbulence in near wall region or the turbulence in outer region or in the buffalo region?
A near wall region, as we
In
can
near wall.
see here, as with the vertical structure. These white guys are quality string vortices, and the number of vortices increased, and also the Reynolds shear stress is increased in the case of uniform blowing.
Okay, thank you. Thank you for your answer.
Maybe in the meantime, I can ask one question, if I may. In the first part of your talk, when you drag reduction with wall deformation, these traveling waves.
Yep.
It appears that when you deform a wall, there will be a pressure component to the drag, I assume.
Yeah.
Now, the drag reduction you talked about is with reference to the smooth wall case.
Actually, in the case of wall deformation, we measure the total mean pressure gradient reduced by the control. So it includes both friction drag and pressure drag.
So my question is, if the Reynolds number is large, the pressure drag, the pressure contribution will be dominant. So will this technique still work in terms of drag reduction with respect to the smooth wall?
I think it depends on the application or geometry of the application. As far as we consider the flat plate as a base case, the same conclusion can be drawn. I mean, the wall deformation is quite small, like 15 wall units. So it should be scaled with wall units. So it doesn't matter so much with the Reynolds number. But of course, if you consider application like black body flow or something like that, then it will be different.
Okay, thank you.
Yeah.
I do have one question as well. You were mentioning the experiments about the airfoil with the blowing and suction.
Yes.
I was wondering how much is the amplitude of the suction in these experiments?
In this case, the amplitude of the blowing was 0.14% or something of the free stream velocity. Very small, very weak.
0.01%.
Sorry, I will check our paper. 0.14%, I guess. 0.14%.
That is very small. Interesting. Thank you.
Yeah.
Do we have
Sorry,
any other? Yes.
May I also ask a technical question on the blowing the airfoil?
Yep.
So my question is, how did you manage to blow the air in a uniform way?
It was very difficult to do that. Actually, we have tuned the cavity, the structure inside the cavity manually and tested many times so that the uniform blowing can be attained. We use sponge and also perforated plate and so on.
And if I may ask, did you regulate the pressure and the flow rate, or just one parameter was fixed?
We fix the flow rate using external pump and flow meter and regulator.
Okay, thank you so much.
But it was very tough to ensure the uniform blowing. We took movies with using particles, and we ensured that the blowing is done really uniformly at the end.
Thank you.
Yeah. not
we
we,
have
but
any-
my student actually did it.
Are there any other questions from the audience? While we're waiting, let me just ask one more thing. For these cases, the CF of the controlled case, how is that measured? Did you measure it directly, or is it from the velocity profile?
This was also another difficult part of this research because we cannot directly measure the friction on the wall directly. We have to estimate from the velocity profile.
Yeah.
And in the case of blowing, as written here, we made a transformation by the modified Stevenson law, then fit it to the Nichols law of the wall, which also accounts for the pressure gradient. So it is kind of technical, but we have confirmed that it is not that bad as compared to the simulation. So we are now believing this technique.
Thank you.
Hi there. May I ask a brief question?
Yep.
Thank you for the talk. In a follow-up to Aman's question earlier about the slide with the model at the higher Reynolds numbers, I have a brief question as to what you think the primary drag determining mechanism is for the larger Reynolds numbers, because I'd imagine that we should consider both the pressure drag and modification to the turbulence, and that would also depend on the wave speed. So could you comment a little bit briefly about that, because I'm not sure what this model is doing or predicting? Sorry.
Yeah, actually, this question is quite related to the previous question, but actually the pressure drag is not a major issue in this case. And in this model, we just scaled the velocity profile like this, and using the macroscopic balance, we derived the equation to predict the drag reaction rate. So we do not explicitly consider the pressure drag in this case.
Okay, thank you.
Thank you. I think we
Just
have
to maybe quick question for clarification. So the flow remains always attached at the wall, or it's never separated at the higher Reynolds number simulations or experiments you did? It's always remains
in
attached?
this case,
I'm saying in general. I mean, in terms of applying this strategy for higher Reynolds number.
It is always attached.
It's always attached. Okay.
Yeah, if separation happens, then the flow will be destabilized like this. So we avoid such high amplitude of the wave.
Okay.
So in the case, as we can see here, like this, when the deformation amplitude is higher than this threshold, it becomes unsteady, and eventually drag will increase due to the pressure drag. We are not considering that region.
I think we have no other questions. So thank you again, Koji, for the very interesting talk.
Thank you very much.
Thank you.